In this video, we're going to talk about how to take partial derivatives of functions. So when we have a function of several variables, we can take the partial derivative by differentiating the function with respect to one of the variables and treat the rest of them like they're constants. Okay? That's how we're going to take our partial derivatives. So there's several different notations for partial derivatives of a function. So the two most common are using this subscript notation, so f sub x sub I or f sub whatever the variable name is, or this partial symbol, partial of f with respect to x. So it looks like a df dx, except that it's a funky looking d rather than an actual d. There are other notations, but these are the two most common ones that we'll see. So this example tells us to take the partial with respect to x and the partial with respect to y. This should say f of xy equals y squared times sine of xy. So this should be f of xy. All right, so take the partial with respect to x. We treat y like it's a constant here and here, right? So this y squared does nothing for the derivative. It just hangs out because it's constant times the function, so we'll have constant times the derivative. Sine of xy, we'll use chain rule. Derivative of sine is cosine. Differentiate the xy with respect to x, and you get an extra y. So that's why it's y cubed out in front. For the partial with respect to y, we now have two functions of y multiplied by each other. So take the derivative of the first, that's 2y times the second, and then plus the first, which is the y squared, times the derivative of the second. And just like when we did the partial with respect to x, we have to use a chain rule. Derivative of sine is cosine. Derivative of xy with respect to y is x. So that's where that extra x out in front is coming from. Well, once we do first partial derivatives, we can do second partial derivatives. So let's look at this function f of xy equals x squared e to the 2y plus log x. Derivative with respect to x, I'm using both the notations here just to try to get you a little bit more used to them. We take the derivative of the x squared. The e to the 2y is just a constant as far as that x squared is concerned, so it just goes along for the ride. And then the derivative of the natural log of x is 1 over x. For y, the natural log of x term goes away because that's just a constant as far as y is concerned, and the derivative of the constant all by itself is 0. Here, the x squared will hang out because it's constant times a function, and then derivative of e to the 2y is e to the 2y times 2. All right, let's look at our second partials. Well, I could take the partial with respect to x and differentiate it with respect to x. So here's the subscript notation for that. Here's the Leibniz notation for it. Much like when they have the d dx notation, the squaring, it's not really squaring, it's second derivative, but the squaring goes on the d part for the top, but on the x part for the bottom. That's just the notation. The reason for that is because we're really talking about how many times this operator got applied. You're doing d dx of d dx of f. So that's why it's just the d's that have the 2 on it and not the f. All right, again, going back up to the partial for x. This 2e to the 2y is a constant. Differentiate the x, you get a 1. So you just get 2e to the 2y. This is x to the minus 1. Its derivative is minus x to the minus 2. Going for the partial with respect to y twice. The only thing that we see has a y here is this one, so the 2x squared will hang out. Derivative of e to the 2y is 2e to the 2y, and that's where the 4 comes from, because it'll be the 2 times the 2. There are two other partial derivatives, though. Notice that your partial with respect to x is a function of x and y. Likewise, the partial with respect to y is a function of x and y. These are functions of two variables. So I can take partials of x with respect to y and the partial of y with respect to x. Okay? The reason why I want to do this, besides doing the extra practice, is also the notation. Notice that when we have f sub xy, this is take the derivative with respect to x and then take the derivative with respect to y in that order. The Leibniz notation is backward. Well, what seems backward? It's dy dx, or partial y partial x on bottom. You do the x first and then the y. The reason, again, that it's written backwards is this is really shorthand notation for a function notation. Again, saying d rather than partial each time, it would be ddy of ddx of f. So the ddx is on the inside, even though you're doing the derivative of that with respect to that variable first. Okay, so this says go back to the partial with respect to x and differentiate now with respect to y. Here's your partial with respect to x. This doesn't have a y in it. It goes away when we differentiate. 2x goes along for the ride. Derivative of e to the 2y will be 2e to the 2y again. So that's why this is a 4 here, because of the 2 times 2. This one says go back to the partial with respect to y and differentiate it with respect to x. Well, the only thing that has an x in it is this piece. The e to the 2y will hang out for the ride. 2 times 2 gives me 4, so I get 4x e to the 2y. And notice that these two are the same. Good news is that in almost absolutely everything that you do, those two will always be true. And what I say is f is nice. The definition of niceness is that their partial derivatives are the second partial derivatives are continuous on a disk around a point. It's what's known as Claros Theorem. Okay? But in general, unless you've got some weird piecewise defined function thing going on, this is always going to be true. If you know how to do one, the other one has to be identical. So actually, it's a nice way to check your work, making sure you're doing your derivatives right. Okay, so that's exactly what Claros Theorem says. If the mixed second, we refer to these as the mixed second partials, are continuous on a disk that contains the point AB, then the second partials are equal at that point. All right, last example here, let's do one with implicit differentiation. Let's find partial with respect to x and partial with respect to y if this relation is true. Now, much like what we did for derivatives, implicit differentiation back in Calc 1, we're going to do the same thing here. Treat z as a function of x and y, and let's differentiate both sides with respect to x first. Y is a constant, but z is a function. Okay, so this first one we have a product rule with the x squared and the z. The y will hang out in both terms. Derivative of x squared is 2x. Derivative of z is partial with respect to x. I don't know what it is. It's an implicit function. It's not explicitly written. So there's a product rule there for the first term. Second term, notice that there is no z here. So I just have to differentiate this with respect to x. Chain rule. Derivative of cosine is negative sine. Derivative of x is 1, and derivative of y is 0. So this is just 1 times the exact same thing we just said. Here is e to a power. Derivative of e to a power is e to that power times the derivative of the power. The power in this case is z. I don't know what z is, so I have to write partial with respect to x for that. Right-hand side is a constant. Its derivative is 0. And now it's just an algebra problem. Collect your the terms that have the partial in it, and factor it out and divide. So the exact same process for the partial with respect to y. We just have to differentiate a slightly different. Well, it's not even differentiating a slightly different piece. It's just instead of writing the dz or the partial with respect to x, we're going to write the partial with respect to y. Here we have y times z, so we have to use a product rule. Derivative of y is 1. Derivative of z is partial with respect to y. So that's where those two terms come from. This is still going to be minus sine of x plus y, because again, there's no z's in here. Derivative of x in this case is 0. Derivative of y is 1. So we just have 1 times that. Notice this last term looks a lot like the last term for x. It's just now with respect to y, because it's the same type of expression. We're differentiating e to the z with respect to y. So we get derivative of e to a power is e to that power times the derivative of the power, still a 0 on the right-hand side. And then the same type of algebra, collect like terms and divide.